right. Thank you for the opportunity to speak here. I hope you enjoy my talk. Please.
But actually, Misha, maybe I think you're allowed to have your mask off if you want.
No, I mean,
yeah.
I don't think it changes quality of my speech that much.
Oh, okay, yeah.
Yeah, but anyway, please feel free to ask questions, and I don't promise that I'll answer them, but at least I'll try to point you to where you can look up the answer. So, oh, by the way, this is a laser pointer, right? Oh, good, it works. So, what is that? We want to sit down.
There's a stick in the corner.
I don't want to do that. Oh, great. That's much better.
Low tech doesn't fail.
All right. Thank you. All right. So my talk is based on some papers we wrote recently with my collaborators, who are Noam Hai. He's a PhD student at the Hebrew University of Jerusalem. Suman Chakraborty, he just started a postdoc at Sequoia. And Ritam Sinha, he is a postdoc at the Hebrew University of Jerusalem. All right, I hope you enjoyed the talk. Broadly stated, I'm going to just be talking about properties of certain conformal field theories. I'll give a little reminder. So simply put, a conformal field theory is a quantum field theory without a scale. This property of absence of a scale is quite easy to accomplish in the classical level. So what you do is just you write down a Lagrangian and you make sure that there are no massive parameters in there. Your theory can be quite sophisticated, such as QCD and Navier gauge theory or 5 to the 4th theory in 4 dimensions. However, once you move to quantum theory, you notice that your classical scale invariance has been broken, and it's simply broken just due to the fact that your theory gets renormalized. So now it's explicitly dependent on the renormalization group scale. Sometimes, as in the case of non-Navier gauge theory, you get a math gap, and you don't have any math degrees of freedom, which means that in the deep infrared, your theory is just empty. In other cases, you can arrive at a fixed point of RG flow, and then a fixed point is described by an interacting conformal field theory. The simplest example of conformal field theory is a free conformal field theory. Say, take a free massless field. What you can do is that you can deform this free CFT by some relevant interaction, which will trigger an RG flow, and you can end up at a non-trivial CFT at the infrared end of the RG flow. So now you have an RG flow connecting a free CFT in the UV and non-trivial CFT in the IR. CFTs are interesting. So as I mentioned above, they can describe an end of RG flow of a QFT. They're also interesting from the perspective of second-order phase transitions, which describe critical state of matter. We know it's a scale invariant, but as it has been conjectured by Polyakov some time ago, those critical state of matter actually enjoy the full conformal symmetry. So it's not just some mathematical observation with no application, but rather it's something that can constrain observables in your theory by quite a lot. So in 2 dimensions, you are likely to solve your theory exactly, and then in 3 dimensions, using the tools of conformal bootstrap, you can constrain your observables quite a bit, just exploiting the fact that your system satisfies conformal symmetry. And of course, conformal field theories are also interesting from the perspective of holography, so hence idea CFT, and in particular in string theory and the higher spin models. CFT is fully defined by a spectrum of so-called primary operators, scaling dimensions, and operator product expansion or OP coefficients of those primary operators. Primary operators are the ones that transform covariance under the action of conformal symmetry group. Conformal symmetry group involves translations, rotations, scale transformations, also known as dilatations, and special conformal transformations, which are based on the inversion operation. Now, conformal symmetry constrains the form of a two-point function of primary operators. So this is the form for two primary operators O1 and O2 with scaling dimensions delta 1 and delta 2 up to an amplitude. Now, notice you have this Kronecker symbol here, which demands that scaling dimensions of operators O1 and O2 are equal to each other. If you just had a scale invariance but not conformal invariance, that Kronecker symbol would not be there. So you would be able to obtain a non-zero two-point function between two operators with the different scaling dimensions, but it will still behave in a nice, scaling way as a function of distance between the operators. But it will be non-zero for different operators of different dimensions.
Sorry, this is dimensional statement or it's?
It's a general dimensional statement. So the reason you have a Kronecker delta symbol in general dimension here is because you demand that that you have a covariance with respect to inversion transformation or a special conformal transformation. The amplitude C, I kept it here implicit, but usually you can just rescale operators and reabsorb C into the definition of an operator. Sometimes you have to be careful that you do it consistently throughout the entire calculation. By the way, I don't mean to bore you with all the stuff which you obviously very well know. It's just I'm reviewing some aspects of CFTs which are relevant for the future. So it's not just introductory course to CFT. Anyway, also if you demand covariance with respect to conformal symmetry group, you also constrain the form of the three-point functions of primary operators. So here 1, 2, and 3 are primary operators with the corresponding dimensions delta 1, delta 2, delta 3. And a functional dependence of the three-point function is uniquely fixed by the demand of conformal covariance.
And if you take just a scale in there,
You will not get this functional form. It will not be so constrained. Yeah, that's a good point. Yeah, so now you have there's two facts that you can test if your theory is enjoying the full conformal symmetry rather than just scale symmetry by looking at the two-point functions of operators of different dimension and by looking at three-point functions. So if they do not satisfy the form we just discussed, then you rule out the statement that you have a conformal symmetry. If they do, then you don't rule it out. You have some sort of a supportive consistency check. You have a conformal symmetry.
Okay, may I ask you about this two-point function? That can you hear me?
Yeah.
No, I just wanted that. I mean, if you have some number of operators with the same anomalous dimension, right? Then I believe that you can diagonalize it, right? Because it's a mixing of them. So you can go to the set of, where it would be, kind of a diagonal operator where it would be just Kronecker symbol in full sense of the word, right? No correlators between different one and correlator only, operator to itself. Is it true?
Yeah, that's correct. So I think it can be generally phrased as a mixing between operators.
Yeah. So, no, exactly. It's what I'm asking about, because in this way, I mean, okay, it's kind of up to the diagonalization, right? Essentially.
That's correct. That's correct.
Okay.
Thanks for the question. All right. So now you see I kept here this amplitude of the three-point function. It actually reappears in the OP expansion of two operators. So when you perform your calculation, it's important to actually do not neglect this coefficient A. So don't be satisfied with just a conformal form of this three-point function. Instead, calculate the coefficient, the amplitude A, because it will tell you how the OPE product of two operators behaves. And if you know OP expansion, and the reason for that is that if you know OP expansion, then you can calculate any correlation function just by substituting the OP expansion to correlation function. All right, so other operators are in the CFT are descendants. Generally speaking, they're just obtained by acting with the total derivatives on the primary operators. And therefore, in particular, correlation functions involving descendants can calculate extracted from correlation functions involving primaries just by acting with the derivatives on those correlation functions.
Where did you assume in the previous discussion that you were dealing with primaries?
Well, for instance, here in the 3-point function, the 3-point function for the primaries, if you act say with derivatives on any of those operators, you spoil the form, the function form on the right hand side. And in general, yeah, it's a good question. So in general, it's assumed because you demand that your correlation functions are covariant with respect to conformal transformation. So you know that primaries transform in a certain way under conformal transformations, descendants do not.
But when you are having this primary operator, let's say that you added primary operator to your Lagrangian, okay? Then often you will get kind of this primary operator can give you massive deformation of your original conformal theory, right? So it would be massive theory which you can view as kind of perturbed conformal theory. So in this way, you are still sitting in the conformal basis, but not going. No, I mean, you see, because in principle you can sum up, the primary operator and get a massive theory as a result.
Right. Yeah. Good point. So yeah, you can deform. You start with CFT, pick an operator and deform your CFT by basically adding that operator the new term. I'll return back to that. That's a good question.
Okay.
It's actually going to be covered somewhat in subsequent discussion. Thank you. All right. Okay. So some simple jargon that people call CFT data, collection of all scaling dimensions and all OP coefficients of primary operators. And to solve CFT means to determine all the CFT data. Once you know CFT data, you can calculate all observables, i.e. all correlation functions of primary operators.
But in APE data, you're implying that it is kind of, you wrote only, say, kind of, you are saying that this operator could be any dimension, right? So there's additional one. So in principle, your APE could go by dimension far away, or I mean, I wonder, what are limits for dimension of those new operator which appears as a product of two? What are constraints?
Yeah, so I mean, if probably stated in a slightly ambitious way. So I'm saying that to solve CFT means to determine all the OP coefficients, but in practical cases, you'll have to stop somewhere. So you'll calculate only so much.
I see.
Right. So I mentioned before that conformal field theories are quite useful because they describe critical states of matter. And the one thing about critical states of matter is a phenomenon of universality. So universality means that different systems under when they put on the phi space in a state of second order phase transition, they exhibit the same behavior quantitatively, the same scaling behavior with the same scaling exponents. And this is true, for instance, for liquid vapor second order phase transition and ferromagnetic paramagnetic phase transition. And you can see it in the behavior of and a scaling behavior, the function of temperature of these observables. And this is a powerful behavior with the same exponent beta, which is roughly 0.33. M is magnetization and raw densities.
So liquid vapor transition at a certain pressure?
Yeah, at the second order phase transition. Yeah, the critical point on TP phase plane. That's right. All right. From the perspective of field theory, you can explain this universality in the following way. So say you start with two Lagrangians, which are microscopically different. So they look quite different. But if the difference between them boils down to irrelevant operators, then they will converge to the same CFT at the end of their respective RG flows. So such systems are said to be in the same Universality class. All right. So I already mentioned before there's a ferromagnetic phase transition. A simple model to describe it is a Ising model, which is quite well known, and it describes spins on a lattice interacting with their nearest neighbors. So here are the angular brackets stand for nearest neighbors. You have spins sitting at the size I and j, blah, blah, blah. And there's the Hamiltonian, and j is equal to 0, so that you have a ferromagnetic state with the order state of have the lowest energy. And you can study that model. You can solve it exactly in 1 and 2 dimensions. You can study it numerically in 3 dimensions. But interesting thing is that you can also have a continuum limit of it given by a scalar field theory with a quartic interaction.
Does that have to be in the same dimension?
Yeah, they have to be in the same dimension. And the most motivated and unsolved case is a 3-dimensional case, in which case when G4 is large, so your system is strongly interacting. This shouldn't come as a surprise. Some of the most interesting phenomena are characterized by strong interaction. This is good in holography because then you can just say, hey, my theory in the bulk is described by possibly classical gravity. And in fact, as you know, the whole industry of idea CFT, people start with some phenomenological theory in the bulk, then they derive observables and they say, hey, this sort of looks like what's really happening in nature.
But in case of Ising model, I believe that it's kind of integrable, right? It is and I believe that in certain way it could be compared with free fermions. So it doesn't look like a kind of, effective strong interacting theory, or I could be wrong.
Right, I believe you're referring to 2 dimensions, right?
Right. Yeah, but you mean in different dimensions. Yeah,
I
I see.
mean 3 dimensions. Yeah.
I see. Okay, good.
Yeah, that's a good point. All right. Yeah. So it's going to hold, but in QFT, in standard 1 QFT, this is there's not something to be welcomed. There's a strong interaction, and in particular, I briefly alluded to it earlier, and I'm not really going to discuss it a lot in the future during this talk. Is people take advantage of conformal symmetry by again 3 dimensions in this conformal bootstrap program. Now, okay, so one of the approaches to deal with strong interaction is the Epsilon expansion. It was used originally by this gentleman, Wilson Fisher, in 1922, to do expansion around 4 dimensions, but subsequently, in particular, later on in the talk, has been applied in other situations. So what one does is that one begins with somewhat esoteric case of 4 minus epsilon dimensional theory, and just proceeds with the calculation, a perturbative calculation, and arrives at the conclusion that the system, the 5.4 theory has a fixed point at the quartic coupling of order epsilon, and that's great. So it means that it's small, perturbative calculation is justified. And then one can study the corresponding fixed point. So derive a CFT data in Epsilon expansion. In the end, you can say, okay, fine. So we derived all of that. Let's set epsilon 1. That will give us 3-dimensional physics. And interestingly enough, the result is quite well in agreement with the experiment, which actually got Wilson Nobel Prize. But don't use it as a criterion in general. Okay. Another tool to study strong interaction is given by 1/n expansion. So 1/n expansion is quite well known, more largely due to original observation by Hoft that if you start with a QCD, which is non-abelian gauge theory, the C3 gauge group, replace it with SUN, and subsequently take the limit of infinite n. So if you do that, then you can observe that a bunch of diagrams seem to drop out, so-called non-planar diagrams, which simplifies your life a little bit. And of course, ADS-CFT again attracted a lot of attention to large n stuff by mapping, taking an infinite large n limit to suppressing quantum effects in the ADS bulk. In three-dimensional Chern-Simons theories, in particular coupled matter, large n methods also receive plenty of attention recently. However, in the context of vector models, the history of large n also dates back quite a bit. And what you can do is that you can simply take your Ising model and replace the scalars S on a sides, on the lattice sides, with unit vectors. So now here S is a unit vector with n components.
So it's an angular momenta or this?
A spin, yeah.
So one can be here.
Yeah. Precisely. Yeah, and you retain nearest neighbor interaction. So it's basically like Ising model, except that I think in three-dimensional cases. Yeah, in three-dimensional cases, Heisenberg model. That's correct. And
but this spin should be viewed as just, kind of, I don't know, n-component scalar field, or how I should view it. I mean, they are not function of x, right? So it's just your variables, or what? I mean,
they are a function of, so in the discrete case, they are a function of index of lattice side, so a function of I, but
yeah.
they are in the rotation group.
Right, but when you call it spin, so I do not see I do not see any fermionic nature in this, right? It's just kind of classical field, right? Whatever, some field with n component or at which point, right?
That's right. It's probably more adequate to call them like a vector multiplet.
No, it's I wonder. So in this way, just you can say that it is a kind of n-component scalar field, right? In certain sense.
Yes. That's correct. That's a scalar field with n components. So it's just a multiplet and with n component multiplet. Yeah, that's a slightly poor choice of wording on screens. That's correct.
Each point has exactly one occupation number of one.
That's correct.
One.
That's correct.
Mm-hmm.
All right. So the continuous version of the stuff is generalization of phi to the 4th theory. So what you do is that before we discussed the phi to the 4th theory, the simple scalar phi to the 4th theory. Now you can have its immediate generalization, which is obtained by taking a free scalar multiplet phi I with n components and deforming it by quartic interaction. But now quartic interaction, in order to respect ON symmetry, so this model is ON symmetric, it will have the following form. So it's basically phi squared.
But you are not putting conditions that the length is 1, or you do?
No, but that's a good question. So I don't put this condition, but anything derived for this model is the same as the sigma model. So it's in the same universality class as the sigma model.
Mm-hmm. So you mean that you could put this condition as well? What?
Yeah.
No, because I'm asking because in normal sigma model with this condition, even without any G, that there is phenomena of appearance of it is a system in some coupling, and then kind of extra field appears because of some coupling in the model. It's without instead of phi to the 4th, they just this condition that phi square equal 1 plays a role.
Right, you're referring to the Lagrange multiplier field, right?
Yeah, right. Yeah, no, it's what was done by Belikov long ago and other people, that's
right. Yeah, it will come up. I'll discuss just in a bit I'll discuss Hyperstatus Transformation, so it will come out. All right. One other thing I wanted to mention about this Lagrange is that here G is a so-called Hoft coupling. So you see this 1 over m factor is explicitly separated from. I mean, the true coupling is G over n, but in the large n limit, this G will be of order 1, and this is something you want to keep track of because this is the whole point of large n limit. So when I see what is the relative strength of different contributions when n goes to infinity. So now in this Lagrangian, you see that each term is of the same order, n squared. Sorry, n when n goes to infinity.
And you implying that dimension of in which dimension you are working now? I mean, when you are writing scalar field, what is your dimension?
Yeah, that's a good question. I should have mentioned it. So it's general dimension for now. Let's say between 2 and 4, but we'll discuss it. We'll discuss it more details in the future.
Mm-hmm.
Okay, so 5 to the 4 interaction, or should I say 5 squared interaction, is a particular case of this of the double trace interaction. Slightly started to discuss before, but so what happens is that let's say you have a CFT with some operator O, and let's say that CFT has ON symmetry and O is ON singlet. So if O has a dimension delta which is less than d over 2, then you can deform your CFT by the operator O squared, and it will activate an RG flow. Now O squared is a double trace operator because O is a singlet, so it's like a trace operator, and O squared is a double trace operator. And if n is large, then there is quite a general argument which you can make using a so-called Hyperstatus transformation by this gentleman, that your theory will arrive at a new fixed point in which dimension of O, instead of being delta, will be d minus delta. So Hyperstatus transformation is a very straightforward mathematical trick. So what you do is that you insert 1 into the path integral, but you represent that 1 in a fancy way. So you represent it as a Gaussian integral over some field sigma. So here also shifted sigma by some stuff for the future convenience, but it doesn't matter. You can reabsorb it into the integrated variable. All right. So if you do that and you combine all the stuff you have in the exponent with Lagrangian you had before, then you say that you see that your model is equivalently described by this that. All right, that's some glitch. I will go away. Anyway, yeah. So now you can equivalently describe your ON model, ON vector model in terms of the following Lagrangian. Now, you have an equation of motion relating sigma and phi. And this equation of motion is true as an operator equation. What it means is that when you calculate curvature functions, anytime you have sigma, you can substitute phi squared and vice versa. And you will not change curvature functions except for contact terms. And you don't really care about contact terms because in a CFT, you're usually interested in curvature functions for operators located at different points. And another thing I want to mention that I'm not going to be, I hope it doesn't cause a confusion, but I usually skip this ON indices business and just write, say, phi as phi squared, etc.
But sigma doesn't develop.
Sigma develops a non-local kinetic term.
One loop it can do.
Yeah.
But it will be singular in sigma, right? Depending on dimension of the space-time.
Yeah, so right. So the kinetic term, the local kinetic term for sigma, I will explain it. I'll explain it in a bit. You'll get a scaling dimension for sigma, which is independent of d.
But look, phi square equals sigma is kind of just notation, right? Essentially, you can always call phi square equals sigma, and essentially what you did by this transformation, right? The question then is that I don't know, kind of in this sense, when you have kind of non-trivial dynamics because compared with this ON model, sigma model, where you have d mu phi square with condition phi square equal to 1, right? Then new field which appears in this model, it would be not phi square, it would be d mu phi square would be essentially a new field, right? Not so in difference with example you're considering.
Yeah, I think I know what you mean. So are you talking about two-dimensional case?
Yeah, 4-dimensional.
Good. Yeah. In two-dimensional case, yes, I agree. In two-dimensional case, sigma. First of all, in two-dimensional case, the theory is free.
Yeah. Okay. Right, but in 4-dimensional case, you are saying that it's still what I'm wondering about whether it's kind of how to say new field appears in the theory or it's just notational. Because in terms of Lagrangian, of course, you can call phi square equals sigma and write what you wrote for Lagrangian. Right, there's no problem with that. But dynamically, it's indeed kind of appearance of a new field, or what's going on?
Well, that's the point. So the point I'm trying to make is that sigma is an outcome of a mathematical trick. In particular, it's not for an accident I mentioned before. This paper, a general paper talking about double trace.
Okay.
Deformations, and then they use the Hyperstatus Transformation to illustrate what happens to the scaling dimension of some general operator O when you flow from V to the IR, and they use Hyperstatus Transformation for that purpose. But in this case, this proverbial operator O is phi squared. So we will be talking about what happens to the dimension of phi squared when we flow from the UV to IR. And a quick handle on how to derive it is to look at what happens to the sigma. So the same as in Goop's and Klebanov paper, except it's slightly more specific in this case.
Okay.
Oh, okay, that's what I just said. So right, so if you calculate sigma correlation function, extract.
Yeah, no, because you are saying delta phi square equals delta sigma, but there is no independent field. So there is phi square, which is a kind of notationally could be denoted by sigma, right? I wonder if there is then appears a difference between phi square and sigma, right? I mean, between phi and sigma. So because in principle you can consider other correlators which are not expressed as correlator of sigma.
That's correct. Yeah, I mean, I didn't want to go too much into that into discussion of sigma models, but from what I understand, in general, the sigma model is kind of mentioned before. In general, the sigma model is in the same universality class as the point vector model. So yeah, and it's in general, but in two dimensions, in any even dimension, all the stuff is free. And in particular, if you say consider two-dimensional scalar field, it has dimension 0. So the only way to construct sigma out of it is to involve derivatives, right? So use something like
yeah, sure,
something like that. What you mentioned before, and this is fine. So this is, but I was planning to not spend too much attention on it because in two dimensions it's just free anyway. So why? Yeah, that's why I didn't want to discuss it that much. But that's a very good point. All right, so let's review something we already briefly discussed above. So let's see. So we start. What is essentially happening? That we start with one vector model. Let's say originally phi is free, so we just have a kinetic term, and the phi has dimension of free scalar field in 2 dimensions. This one. So phi squared is just double of that, just t minus 2. Now, if you turn on phi squared instruction, you float an interior fixed point in the IR. You can calculate what is the dimension of phi squared in the IR. So that's the same as dimension of sigma, and it's actually 2 up to 1 over n corrections. So you see that phi squared operator acquires an anomalous dimension that's the leading order in 1 over n expansion.
You just integrate out, right? What you do
You integrate out 5.
Out the 5 field,
That's correct.
leading contribution in N is just one loop. And then you get a potential for the sigma, but it only depends on the number of dimensions. So I want you to tell us finally, in which number of the space-time dimension will you work or do you?
Okay, so far I'm in between 2 and 4. So it's general D.
No, 2 is not working. Because scalar field in 2 dimensions is ill-defined, right?
Yeah,
you cannot work with it because it's,
this one.
it should have one.
All right. Yes, sorry. I mean, I should have made this point.
Is equal to 3. You can solve it.
Yeah.
You tell us, I work in 3 dimensions.
Well, that's not quite true. So let me comment on that. So I do not work in nowhere in this nowhere in the calculation performed in a large n limit, you actually have to fix that d is equal to 3. You can calculate it in general in d is equal to 3. You might as well calculate it in general d as a function of d. And
but we don't have in nature any space with a non-integer number of space-time dimensions.
That's correct. That's correct. But you see, that I'm discussing later in my slides. So that's a good point. We're kind of jumping ahead, but I would just answer your question. Then once I arrive at the corresponding slide, we'll discuss it. So the answer is that before I mentioned the Wilson-Fisher Epsilon expansion, which is specifically designed to work in 4 - epsilon dimensions. Now, imagine you derive something in 1/n expansion, and you want to just compare it with what other people derived, say Wilson-Fisher. So now you can do that because you derived your result in general D. You can algebraically expand it around 4 dimensions, and then you can take what Wilson-Fisher derived around 4D and derive that in 1/n, because their result is exactly for all n. And then you come.
So your final goal is to do the 4 - epsilon case and then tend epsilon to 0.
That's not my final goal, but that's something which allows you to compare what you derived with what other people derived. So it gives you a consistency check of your result. So if you just derived it in d is equal to 3, then you as I mentioned, you might as well have derived it for general d as a function of d. And if you have done that at no extra cost, I'll skip a joke here, but at no extra sorry, you derive it in general d at no extra cost, at no more effort than fixing d is equal to 3 at the outset. But now you can also expand it around 4D and compare it with Wilson-Fisher. So you can do a consistency check of your formulas.
Okay.
Yeah. Sorry, maybe I'm not explaining it very well, but there is another slide further on that I'll try to reiterate this point. Yes, please.
Can you comment a little bit on the history? So like, where are we in history right now? So like, when was this these remarks first made? I mean, is this old?
Yeah, that's a good question. So I have, as you noticed, I have some references in my slides, but you know, there are a bunch and a bunch of works. The stuff is like from the 80s, and
okay, good. That's what I was.
Yeah, yeah, and it's a I don't know. It's my.
Tell us when you start when you start reporting on something very like new.
Yes, I will. Yeah, I mean, I'm reviewing all the stuff. It's not just randomly selected from the history of physics. I'm just reviewing stuff which is going to be relevant for what is new. Yeah. Thank you for your question. But in general, I feel like it's impossible to do justice to citing everybody the way you do in a paper. Yeah. All right. Okay, so we just derived the dimension of sigma in the R is 2. So at the leading order in 1/n, you get you quickly conclude the dimension of sigma squared is 4 plus 1/n corrections, and that's an interesting observation, because now you see that you can drop the sigma squared term out of your Lagrangian if you care about terms which are relevant in the IR for dimensions between 2 and 4. So what you're left with is that you're left with the following Lagrangian, which describes your infrared CFT, and plus you have a prescription for what's the propagator of sigma. So it's It's a primary field with dimension 2, and you know what its propagator is from other calculation. Okay, so this is about Mikhail's question. Let me try to reiterate it again. So I hope I will be able to explain it. So far, I mentioned two techniques of calculation. I mentioned epsilon expansion and 1/n expansion. They're complementary to each other. You can do epsilon expansion taking advantage of the fact that the theory is free at even dimensions and slightly relevant near even dimension, or you can do 1/n expansion without caring about what dimension you're in. And these two results are complementary to each other because you can cross-check them in overlapping regimes of validity. So what you do, please don't read this. So what you do is that you take stuff which you derived in epsilon expansion for the vector model for arbitrary n. Say you derived some scaling dimensions, you derived some OP coefficients as a general function of n. You don't need to take a large n limit in that case. So you perform you take a large n limit. You perform 1/n expansion to any order you want. It's just an algebraic expansion. It's not a perturbative expansion. Analogously, you can take the stuff which you derived in 1/n expansion, but in general D, and expand it in epsilon near, say, 4D. Again, you can.
But when you're doing expansions, then you should say something about the product of epsilon multiplied by n, right? Because you know, I mean, you have when you have two small parameters, you know, you can then result could depend on the order of limits, right?
That's correct. Yeah. You do it in a careful way. So
no. What means carefully? It's still different limits. Either epsilon multiplied by n goes to 0 or goes to infinity, right? Or fixed.
Well, I think in this case, I agree with what you say in general. I think it's true in general. In this case, you don't have to. It turns out you don't have to worry about those others. So those limits commute with each other. So my statement is that.
Okay, but then you are saying that there is no this phenomena of different limits, right? So you are saying that this way there is a consistency in certain sense.
Yeah, precisely. Yeah, my statement is that in this case, those two limits commute with each other.
I see. Okay, good.
Yeah, that's a good question. All right, already explained that. So, all right, I'm not going to go to any details of the calculations. You could see them in the papers, but basically the general idea is the following. So we are doing a conformal perturbation theory. The expansion parameter is 1/n. So it's an large n limit. This is our Lagrangian. We already saw it above. These are Feynman rules. So here we know everything. We know there's a free propagator, large n propagator for phi, large n propagator for sigma, and the cubic interaction vertex. And we know the dimension phi, and the dimension of sigma is now 2. And elsewhere, we also calculated the amplitude, so don't worry about that. And
excuse me.
Yep.
Why cannot? Okay. If sigma is x independent, it acts like a mass term, right?
That's correct.
For the phi.
That's correct.
But sigma may not be necessarily x independent.
Precisely.
You will need the vertex on the right hand side.
Precisely. Yeah, that's correct. Yeah, as I mentioned previously, I actually could have. The whole stuff can be equivalently reformulated by integrating out phi and just writing down effective theory for sigma as a field, not just a constant and effective potential.
So sigma will never have, in your consideration, sigma will never have a wave.
That's correct. That's correct. It's conformal theory. All right. So some basic tricks in a perturbative calculation position space. Again, this is all stuff. I'm just I'm not planning to explain to you the details of any calculations, but a brief review of the tricks which people usually use in this case. So first of all, loops in position space are just additive. It's very simple. You have two propagators, 1/x to some power times 1/x to a different power. You just add the powers. if you have two propagators connected to the vertex, the power is again each determined, just sum of the powers minus the integral of the vertex times some function. Don't worry about what it is. And one very, very useful relation which people use in such calculations is a so-called uniqueness relation or star triangle relation. It's how to integrate over a vertex, over 3-point vertex, such that it is conformal, i.e., such that the exponents of the propagators converging to the vertex is 2D. It's very simple. You can integrate it. You just get this 3-point function with a coefficient. All right. So once you do all those calculations, you discover that that many diagrams are divergent. Now we know that we are in a CFT, so we cannot have any divergences due to renormalization of the vertices. They're all fixed to their fixed point values. But we do have anomalous dimensions. So we have divergences responsible for generation of anomalous dimensions of operators. Anomalous in the sense of anomalous in 1/n expansion, in the sense of corrections to the dimensions due to 1/n effects. Yeah, so a very straightforward way to take care of the divergences is simply impose a sharp cutoff. So bound all of your logarithmic integrals from below by some UV scale, and then subtract infinity at the cost of introducing an RG scale mu. You get those logarithms, and then you can extract all of your anomalous dimensions as coefficients in front of the logs. A more formal way to address divergence of your conformal graphs in position space is to add a small shift called delta to all of your internal Hyperstatus field lines, sigma lines. Also incorporate some powers of mu to the delta for dimensional reasons. You'll get a divergent result of the final answer in the limit of delta going to 0. To subtract those divergences, just perform wave function normalization where gammas are anomalous dimensions. Once you subtract the divergences, you'll get the finite correlators. Now, here you have both anomalous dimensions of your fields and some corrections to amplitudes. Now, remember before we discussed that corrections to amplitudes are unphysical, and they are. However, if you care about calculation of FTPI coefficients, you might want to keep track of them explicitly because you don't want to just erase them everywhere inconsistently. All those rules of perturbation space here and position space, they work equally well both in 1/n expansion and in Epsilon expansion. As I said, I'm not going to discuss any details. All right, so now let's talk about other dimensions. So before we converge to the fact that we are talking about dimension between 2 and 4, what if we want to consider other dimensions? So for one thing, we know the dimension of sigma is equal to 2. Scaling dimension of sigma is equal to 2 in any space-time dimension. We want our theory to be unitary, so we want the delta sigma to satisfy unitarity bound. That puts a general bound above on what dimension we can live in, and it's 6. On the other hand, we know that quartic coupling is irrelevant above 4 dimensions. So that's not something you want to have in general in your QFT. However, since we don't do expansion in G, and we don't even want to, the theory is strongly coupled, we do expansion in 1/n. And in 1/n, perturbation theory in 1/n is actually renormalizable. And now we have this irrelevant operator, so it brings your theory to a non-trivial regime in the UV, but at the IR end of RG flow, it is free. Now, again, so I mentioned before that all this CFT data, when 1/n expansion was derived as a function of D for general D, and I mentioned the advantage that you can compare what you derived with Wilson-Fisher expansion around 4D. Another advantage is that now you can just analytically continue to higher dimensions.
But you mean that 1/n perturbation theory is generalizable for D larger than 4?
That's correct. That's
Right.
precisely correct. It would have an issue at D larger than 4 because that's where phi to the 4 is a non-normalizable, is an irrelevant operator. But if you do expansion 1/n, then it's renormalizable.
No,
Because
okay. So you are saying that higher dimension operator for d equal d larger than 4 contains 1/n suppression?
Absolutely.
Mhm.
Absolutely. All right. So, however, that's not where problems with higher dimensional theory stop. It's not just an issue of being non-renormalizable. So the other issue that remember that we discussed with the Fisher fixed point, and we got that we reviewed that fixed point value of the quartic coupling is behaves as epsilon times some positive number. You could have done the same thing formally for 4 plus epsilon dimensions. Then we get that now the coupling constant is minus epsilon, which is a catastrophe because now you have a runaway behavior away from the vacuum phi equal to 0. So you see it is unstable. It's actually unstable in the entire range of the higher dimensions. So
When you say it's unstable, do you just mean it's not a CFT?
I just mean that it doesn't have a stable vacuum. So one of the usually implicit assumptions you make discussing CFT is that you have a stable vacuum. So you're going to have the states obtained by O times 0, where 0 is a well-defined vacuum. So now you don't have the 0.
But the reason I'm asking that in that way is that if the phi equals 0 vacuum is unstable, a possible and indeed a likely seeming scenario, that the vacuum just moves somewhere else where phi has a VEV and conformal symmetry is broken.
That's that.
How do you know there's no ground state? That's
right. That wouldn't be half as bad, but in this case, it looks like it's just a runaway to infinity. I probably shouldn't have said it would be half as bad, but it doesn't look like this is happening now. So now it's just a runaway to phi equal to infinity. It's not like a Higgs or anything. All right. So all this business with somewhat shaky ground of phi to the 4th here in higher dimensions motivated these guys to approach the CFT from a slightly different angle. So they were wondering if you could derive it as a fixed point of a different theory, which achieves non-trivial criticality in the infrared. So what they did was they say, okay, let's study the following organism. We have again phi, which is an ON multiplet. We have sigma, which is a scalar. And we deform this theory by cubic couplings between sigma and phi and the self-interaction sigma cube.
But now you add a kinetic term. So,
That is correct.
whereas before you didn't. It was
That's absolutely correct. Yeah, that's apparently a different theory. So that's why it's so surprising that what follows will follow. So that this apparently different theory actually has the same fixed point as the UV fixed point of ON vector model. This is plagued by instability UV fixed point. Well, I mean, this is also unstable. You have the sigma cube, which is an unstable term. Okay, so duality between two theories starts with matching with degrees of freedom. So phi matches to phi, sigma matches to sigma. So I probably should have used different notation, but it was mentioned before. So if you have two theories which are different at the Lagrangian level but converge to the same critical regime, it's called universality. In this case, it's they also call it a UV completion. Because this theory goes to critical regime in the IR, or the model goes to critical regime in the UV, so they meet in the middle. So this one is a UV completion of an vector model.
But is it okay with sigma cube term?
No, it's not. Yeah, that's
precisely
that's this theory manifestation of instability.
It's unstable.
That's correct. That's absolutely correct. All right. So those cubic couplings are slightly relevant below 6 dimensions. And you could do perturbative expansion with sufficient style below 4 dimensions. And people actually invested quite a lot of effort into that, doing calculation up to 4th order in perturbation theory. And then you start wondering, okay, so how will you go about proving that the CFT you obtained is the same as the ON vector model? just expand it to 1 over n, and compare it with those general D expressions which people derived for the ON vector model, but expanded around 6 dimensions. So actually, gamma phi in 1 over n expansion, I think it's known up to 1 over n cube, and gamma sigma is known up to 1 over n squared as a function of D. Take those, expand them around 6 dimensions, compare what those gentlemen derived, but expanded in 1 over n algebraically.
I have a naive question. This condition for weak coupling is assuming like fixed n. But if you take n, is that correct?
It's assuming a finite n. That's correct.
Yeah, right. But if you take n to infinity first, is there a different condition for when the theory is decoupled or no?
I don't believe so. I think that the coupling. Yeah. I think the coupling that scale with 1 over squared over n in the leading order. So it's even better.
Thank you.
Yeah, thank you for the question. All right, so compare the results, you get a match. So everybody is happy, in a sense. Okay, so new topic. What you can do is, remember we started talking about Ising model before. Ising model has a nearest neighbor interaction of spins on a lattice. So some time ago, quite a long time ago, it was proposed by Dyson to describe one-dimensional ferromagnets by generalizing Ising model in a long-range sense. So by replacing nearest neighbor interaction with a power law decay of interaction as a function of a distance between the spins. This power law decay is controlled by this parameter f. And then people studied it in general dimension between 1 and 4. Okay, this might appear somewhat obnoxious, but we were not the first people. We were not the first people who proposed this model, but and again, there are papers by Gupser et al., and then there are papers by Gayombe et al. So there are preceding works, but we calculate some more stuff for this continuous model generalization. And cited more than adequately in our papers. Anyway, so what you do is that you take your ON model with phi to the 4 interaction, and you substitute the local kinetic term with this bilocal kinetic term, again controlled by this parameter S.
Is it a causal theory?
Yeah, it's a Euclidean theory. Yeah.
It's causality, right?
Yeah, it doesn't have a problem with causality because it's Euclidean theory.
Because usually non-local theories violate causality.
That's correct. That's correct. All right. I paused because I just remembered I wanted to address it, but it's not on my slide. So Tony asked before regarding the sigma, the kinetic term for the sigma. I don't want to jump back and forth, so let's discuss afterwards. I'll mention something else. All right. Okay, so bilocal kinetic term actually fixes once and for all what is the scaling dimension of the field phi. So this isn't going to be affected by any interaction. And then you can use this delta phi to calculate dimension of the quartic coupling constant. You determine that it's relevant when S is bounded from below by d over 2. And if smaller than d over 2, then the infrared theory is just free. Now, the great thing about this long-range business is that you can do Wilson-Fisher expansion for any dimension. The way you do it is that you choose S to be slightly above this lower bound, d over 2. And you perform expansion in epsilon, but now you sit in general D, but you're still in a controlled perturbative regime. Again, you can use Hyperstatus Transformation. So you can rewrite a Lagrangian model in this form, in terms of the Hyperstatus field, and the same old stuff, just extended for large and sorry, it's the same old stuff, just extended for long range case. Is that you calculate a scaling dimension of the operator phi squared. You notice that it arrives your theory arrives at a new fixed point in the IR where its dimension is equal to S as contrasted with dimension d minus S at the free theory, in the free theory. All right. Now, this theory is somewhat subtle because I've been talking about CFTs at the fixed point of a long-range theory, but in fact, you have to be somewhat careful with those statements because since your theory is non-local, you don't have a stress energy tensor anymore. And that's kind of crucial when you want to talk about, generators of conformal transformations. Now, I mentioned close to the beginning of the talk, spent a couple of slides elaborating on reviewing CFT stuff regarding behavior of 2-point functions and 3-point functions and how they're constrained by the conformal symmetry. So remember that if you just have a scale symmetry, but not conformal symmetry, then 2-point functions and 3-point functions are less constrained. So now it's actually becomes relevant because you can see if your theory in fact enjoys the full conformal symmetry by looking at those correlation functions. Those are the consistency checks of the fact that the system actually is described by CFT at the fixed point.
So the fact that you spread this interaction, right?
Yeah.
A little bit. This is like modifying theory a little bit. Probably I don't remember that you deviate from the. I mean, depends on what range of the interaction, right? This non-locality, right?
Yeah.
The two spins interact as 1 over R cubed, right?
But normally you can put them together, continue in order to go to. If you have say continuum limit, and then your kinetic term is expandable in the powers of G5, right? Now, not only it's not expandable in phi, but it's has a singular point when phi of x is equal to phi. I mean, x is equal to y. You cannot have this limit. You don't have this limit in the Lagrange.
Yeah, that's a good point.
Like UV singularity.
Yeah.
Right.
So it's a totally different class of a dynamical system.
That's a good point. Yeah. Thank you for answering. All right. Okay, so those checks of conformal invariance and some general argument for conformal invariance are provided in these works. They are for n is equal to 1 case of Ising model, and then we just added some more calculations for some correlation functions. Most importantly, this one sigma squared sigma, and the 3-point functions to some subleading order in 1 over n expansion. Now, it's not for all S you can have a long-range model for all the values of this parameter S. So one thing we've already discussed how it's bounded from below, but requirement of relevance of the quartic interaction. It's also bounded from above, due to the fact that for large enough S, your model will actually transition to the short-range regime. So you can see it by starting with a short-range model and calculating scaling dimension of bilocal action in that model. So if you do that, you will see that this term is more relevant than the local kinetic term for S smaller than certain threshold value, which is almost 2. So it's different from 2 by slightly below 2. It's different by the anomalous dimension of the short-range scalar field. So this is the range you get, which defines for you the regime of validity of the long-range model. All of the CFT data is expected to be continuous across the long-range, short-range crossover. The simplest example of CFT data to manifest that statement is just full scaling dimension of phi. So in a long-range model, at the crossover point is equal to the full scaling dimension of the short-range field phi. And in one of our papers, we explicitly showed that a bunch of other CFT data is continuous across the crossover point. All right, I would probably want to skip that. All right, so now remember we just derived this bound on the parameter S at which the model is exists in a critical long-range regime of the IR. Now, what if you consider S less than d over 2? Again, in this case, you get 5 to the 4 interaction, which is irrelevant, but it seems to be fine in 1 over n expansion. So in this case, you get a relevant operator 5 to the 4, which drives the theory from a trivial regime in the IR to an interacting non-trivial CFT in the UV. Since we already have all of the results, well, not all of the results, but a bunch of results for CFT data available in the 1 over n expansion in general D, we could just use them and analytically continue them all the way to for S less than d over 2.
I'm sorry, Misha, how much time do you need to wind up?
With any luck, 10 minutes. Yeah, I'm sorry. I'm feeling like I'm spinning over the time limit a little bit. I'll try to skip over relevant stuff. All right, so you want to be in a long-range regime, so you want S to be below the long-range, short-range crossover point. However, S cannot go all the way to 0. It's bounded from below by d over 3. Why? Because if you look at the anomalous dimension of the field sigma, you will see that it's singular at S is equal to d over 3. So you don't want to go below d over 3 because then you'll drop below the unitarity bound. So this is the upshot. So this is the bound you have on a parameter. Oh, by the way, this is the new stuff. So I promise to say when the new stuff begins. So it's like it was somewhat interspersed before when I said that we calculated this and that in those papers, but this is mostly what this talk is going to be about. So basically, this is the parameter S at which the long-range vector model exists in a non-trivial critical regime in the UV. And if you also remember that S star is about to be 2, is about 2 up to 1 over n corrections, you also get a bound on D. So it's between 1 and 6. And now you have a non-trivial critical regime in the UV also for D less than 4. This is to be contrasted with the critical ON vector model, local ON, or short-range ON vector model in the UV. Again, same problems with instability. So you could have done Wilson-Fisher expansion for S to be for S slightly below d over 2. You would get a negative valued fixed point value for the quartic coupling constant. It's analogous to what you get in D is equal to 4 plus epsilon dimensions for the short-range model. So now you're again motivated to talk about this CFT in a slightly from a slightly different angle, but probably get some extra insight. This is a very simple generalization of cubic model we discussed before. So what you do is that you consider ON long range ON scalar multiplets theta, and the local field rho a singlet of the ON group, and you couple them via cubic terms. And the statement is that this model will arrive at an IR stable fixed point, which is described by the same CFT as a UV fixed point of the long-range ON vector model. Again, such a statement of critical duality or UV completion or universality begins with matching degrees of freedom. So you match ON multiplet with ON multiplet, you match ON singlet with ON singlet. Now let's see. So we're going to be solving this model perturbatively in epsilon expansion. So you notice that your scaling dimensions of your degrees of freedom in the UV are known. So the scaling dimension of theta is actually fixed exactly by the Bauer kinetic term. The free scaling dimension of rho is just free scalar. And you also want your theory to be unitary. So this one shouldn't drop below unitarity bound. So S should be smaller than 2. And you also want to be in the long range regime. So S actually should be smaller than S star, which is slightly less than 2. So now you get this bound on S. Additionally, let's look at what happens with the coupling constant. So in the UV, coupling constant have cubic coupling constant have the following dimensions. You want it to be relevant, so the theory follows the non-trivial regime of the IR. So it's both bound on D and on S. So D should less than 6 is something to track of, and we want to do epsilon expansion. So we put D slightly below 6, and we put S slightly above D over 2 minus 1. We'll do expansion in epsilon 1 and epsilon 2. This is the ratio. We assume alpha to be of order 1. So epsilon 1 and epsilon 2 go to 1, go to 0 at the same order. So alpha should be bound by 1/2. So the main claim is that there is a precise duality between a cubic model and the ON vector model in the long-range regime for the entire range. But we're going to be doing a perturbative expansion, a perturbative epsilon expansion mentioned before. So already measure degrees of freedom. So what about dimensions? So both vector multiplets phi and theta on both sides of the duality, they have a fixed scaling dimension, so that they match. And what about sigma and rho? So sigma Hyperstatus field in the line vector model, it has dimension s up to 1 over n corrections, and you can actually argue that rho has dimension s up to 1 over n corrections as well, without doing almost any calculations.
So S again, this is the parameter that enters in the non-locality.
Yeah, that's correct. Let me write it down. So the action includes this term. Plus etc. Plus interaction.
So in real world, there will be some expectation what the S will be if this is like the two spins interacting.
I would think so.
Right?
Yeah, I would think so.
Yeah.
All right. All right. So this is a somewhat educated guess about how the fixed point couplings are going to behave once we expand them in 1 over n. So we don't have to expand them in 1 over n. There's an epsilon expansion. But if we expand them in 1 over n, this is how they would behave. Well, that's pretty easy. It's 1 over n expansion, and the leading order scaled as 1 over square root of n. And use that. And let's look at the Cowan-Timanchi equation for the rho theta 3-point function. In 1 over n expansion, a bunch of terms drop out, and you get a beta function for the coupling G at a fixed point at 0, and you could derive what gamma rho, anomalous dimension for the singlet field rho, is equal to just epsilon 2. And therefore, the full scaling dimension of the field rho in the IR is S at the given order in epsilon expansion up to 1 over n corrections. So that matches scaling dimension of the Hyperstatus field. So that's a very reassuring sign. Another thing is that now we can calculate scaling dimension of the cubic coupling constant in the IR. Why do we pay attention to that? Because cubic coupling is what distinguishes this model, cubic model, from the ON vector model. In ON vector model, there was no sigma cube term in the Lagrangian, but there is one here. So how to explain that? Well, scaling dimension of the associated coupling constants is d minus 3s, and it is irrelevant and it is negative for s greater than d over 3. So sigma cube is an irrelevant operator in that case.
But this cubic term, it does not give you run away. So it's not that you can make an energy arbitrarily negative and large. No, it depends on other terms. But I wonder, because if it would be just cubic term, it could be, signal of instability, right?
Yeah, actually it is. So the fact that Mikhail also mentioned this before. So the fact that we have a cubic term is actually this model's counterpart of the fact that the high-dimensional vector model is unstable. Mm-hmm. So it manifested quite straightforwardly in this case, and it's manifested like relatively straightforwardly because we have to calculate fixed point quartic coupling in the ON vector model. But here, if you just consider direction of sigma in the negative, large negative values of sigma, and put everything else to be fixed, put phi to be fixed, then you clearly have a runaway behavior to minus infinity. That's an instability. All right, thanks for empathizing. Yeah, and I hope it's not totally hopeless, but what Tony asked before regarding the kinetic term for sigma. So in this model, in the cubic model, you have a kinetic term for sigma. If you calculate its dimension, you can also see that it's irrelevant. So it has a negative dimension analogously to the sigma cube term. So both of them are irrelevant. That's why it's not right. That's why it's not really a problem. That. All right, so we're doing perturbative expansion in epsilon, so this parameter alpha is fixed between 1/6 and 1/2. All right, I'm going to skip that. That's perturbative calculation, blah, blah, blah. You arrive at a fixed point. All right, this is the answer. I'm sorry, I just skipped over over some diagrams. So you derive fixed point values for your coupling constants that allows you to calculate a bunch of CFT data. And all of that is valid for sufficiently great n, where n is a function of alpha. Now, so you're calculating CFT data. Oh yeah, it's a stable fixed point. You can calculate, say, scaling dimensions of the field rho. So above, we already matched those scaling dimensions with the leading order in 1/n. Now we can match them at subleading order, and we actually get precise match. So here, this contribution 1/n contribution actually precisely agrees with what we have for anomalous dimension of the Hyperstatus field. If we knew anomalous dimension for the Hyperstatus field to higher order in 1/n, we could have easily compared it because this is just algebraic expansion. One can also compare OP coefficients, which are extracted as amplitude of the 3-point functions. And that's very easy. It's just three-level diagrams determined by the coupling constants G and H at given order in epsilon expansion. Fortunately, this one was calculated in our previous paper, so we can just take that and take epsilon expansion of it. And we can also calculate look at sigma. That one is known to the leading order in large N expansion. All right, yeah. All those everything we could compare all that CFT data matches on both sides of the proposed duality. All right, so let me just quickly discuss a couple of conclusions and. Recently, there has been some discussion of persistent symmetry breaking, i.e. symmetry breaking at arbitrarily high temperature in vector models, and long-range models play a role in that. There is a fermionic generalization. Obviously, there would be no chance for me to discuss today. It would be interesting to see if that fermionic generalization can play a role in persistent symmetry breaking, which so far has been discussed only in the bosonic context. I skipped over this long range to short range crossover, but it's also a good question whether it can be whether it plays a role in the fermionic case. All right, thank you.
But when it's kind of short range, conformality still keeps there, or it's breaking conformality, breaks conformality.
In which case, sorry?
When you're already in short range.
Right. Yeah, I skipped over those slides. So what's happening there is the following. So you ask a question. If you start with a long range model, so I mentioned before that at some s equal to a star, it crosses over to a short range regime.
Yeah.
And this guy is asking, so what is that short range regime?
Mm-hmm.
And their claim is that it's a short range CFT plus a decoupled generalized free field of certain dimension.
So in this way, it stays conformal.
Yeah, it stays conformal. So it's a short range conformal field theory plus this just generalized free field, and they also said that what's called high. So So they said it's to the right of the crossover as the action. This is the parameter as star is equal to short range action plus the generalized free field action for some extra degree of freedom chi. I think it has a dimension d plus s over 2, so here's d minus s. So they said that, okay, so above s star, chi is decoupled. Chi is also okay, so, above s star, chi is decoupled field. They said that if you go slightly below s star, then you can actually do the following. So you can have a perturbative coupling between above this stuff. Plus, you can have a perturbative coupling between the field phi and chi. And then their claim is that you can do conformal perturbative expansion and find a fixed point for the IR fixed point for the coupling lambda, and the statement is that that fixed point is precisely the long range fixed point. But fixed point then as the long range CFT. But above a star, this is an irrelevant operator, so chi just decouples. This is the content of some stuff I skipped over.
Doesn't have an AES.
I think it's sort of correct unless you refine slightly by what you mean by ADS dual. So if you take into account that your boundary theory doesn't have a stress range tender and find a bulk counterpart of that. Right. Yeah.
I think there were people that liked them.
Right. Good. So yeah, there might be some counterpart of this calculation in ADS, say in ADS space, but I'm not sure if it's necessarily in a holographic context. Yeah.
So it's about the persistent symmetry breaking.
Sure.
So in examples I know of where there's persistent order, there's often like a Hoft anomaly forces the symmetry to break. Is in these examples, is that some of the reason?
Well, in this case, it's the story is the following. So imagine you have some physical system with some order parameter which basically breaks the symmetry at 0 temperature. So now if you switch on temperature, usually what happens is that if temperature is sufficiently high, then the symmetry gets restored. This is especially intuitive if you do have something to define what is the high temperature. So if you have some built-in mass parameter in the theory, then that can define what the critical temperature is going to be. In the CFT case, that's unlikely to be the case. You don't have any mass parameters, so nothing will define any critical temperature for you. So you either have 0 temperature or non-zero temperature. So this business with persistent symmetry breaking is to say that let's engineer a theory that breaks the symmetry at some temperature, and therefore to break symmetry at any temperature.
Sure, yeah. Thank you.
I'm sort of going over time.